Welcome to another deep dive. Today we're taking a stack of your sources, our own research, and really diving headfirst into the fascinating world of AI inference. Our mission today, uncover the secrets to making AI models faster, smaller, and just vastly more efficient, especially when they move from, the controlled lab environment to the demanding reality of the real world. We're tackling a core problem here, what we're calling the AI efficiency gap. See, while training these massive AI models is incredibly computationally intensive, it's kind of a one-time investment. The real recurring cost, the daily challenge, comes during inference actually using the trained model to make predictions on live data. And this is where that gap, between the ideal training setup and demanding production reality truly becomes apparent.
It really is remarkable how large these modern deep neural networks have become, especially things like large language models, LLMs, or complex computer vision models. I mean, you're talking models like VGG16, which can be over 500 megabytes, or BERT base, around 440 megs. And then you get to things like GPT-3 with a staggering 175 billion parameters. It's just huge. This immense scale presents a significant hurdle for real-world deployment, particularly for resource-constrained edge devices. Think your mobile phone, tiny IoT sensors, the computer in your car. They all have limited memory, limited processing power, and crucially, limited battery life. Just the memory footprint alone can often make it impossible to run these giant models directly on that edge hardware.
Right. So this deep dive is going to illuminate how specialized inference runtimes work to bridge this very gap, helping you get the absolute most out of your AI models in practice. Okay, let's delve a little deeper into this AI efficiency gap, because it's truly about more than just hitting a high accuracy score in a paper, right? It's about practical real-world deployment.
Exactly. While training is often a substantial, but one-time investment, inference is the recurring daily cost. Think about large-scale services like chatbots or recommendation engines handling millions, maybe billions of requests every single day. Inference accounts for the vast majority of that model's total cost of ownership over its lifetime, which means the metrics you care about fundamentally shift from training to production. During training, sure, you're looking at accuracy, loss curves, things like that. But in production, you become laser-focused on latency. How quickly can I get a single prediction? Throughput, how many predictions can I crunch through per second? And resource utilization, how much This critical shift underscores that the developer's journey absolutely does not end when a model is trained. It just enters a new, vital phase of optimization and, operationalization, getting it to actually work efficiently.
And this is where the industry really started to innovate, to tackle this problem head on. To bridge this gap, two key open standards and tools have emerged that we need to talk about: ONNX and ONNX Runtime.
Yeah, let's break those down. So first, ONNX. That stands for Open Neural Network Exchange. It's an open source standard, originally came out of Microsoft and Facebook, which is now Meta, of course. And its purpose is representing machine learning models. You can think of it like a universal blueprint, maybe a common language for AI models. It gives you a standard file format ending in .ONNX. And the primary benefit here is framework interoperability. So a data scientist could train a model in, say, PyTorch, then export it to this ONNX format and deploy that same model in a totally different environment, maybe a C# application or a Java backend, without needing to rewrite any code or even install the original PyTorch framework.
So it decouples the training environment from the deployment environment.
Precisely. It beautifully decouples training from deployment, which significantly reduces engineering overhead and complexity. At its core, an ONNX file just describes the model as a computational graph, a series of operations defining the model's logic. And to actually see this graph and understand what's going on, there's a tool called Netron. It's pretty much indispensable for visualizing and debugging these .ONNX files.
Okay, so if ONNX is the model's blueprint, the universal language,
Right.
What's ONNX Runtime? How does that fit into the picture?
Right. If ONNX is the blueprint, then ONNX Runtime, or ORT as people often call it, is the high-performance cross-platform engine built specifically to execute those ONNX models. It's also developed by Microsoft, also open-sourced, and it's battle-tested. They use it in their own high-scale products like Microsoft Office, Bing, Azure Services.
So it's production-ready?
Definitely production-ready. It offers multi-language APIs, Python, C++2, C#, Java, even JavaScript. And it can be deployed on a huge array of hardware and operating systems: cloud servers, PCs, mobile devices, even directly in web browsers. The core idea is actually elegantly simple. You train your model in whatever framework supports ONNX, export PyTorch, TensorFlow, scikit-learn. You convert it to that .ONNX format, and then you load and run it with ORT for accelerated inference. That's the basic workflow.
That makes sense. Simple premise, but powerful. How does ORT actually achieve this high performance, though? What's its secret sauce, so to speak?
Well, its power really lies in its modular and extensible design. When you load in .onX model, ORT first converts it into its own internal in-memory graph representation. Then it applies a series of hardware-agnostic graph optimizations. These are clever tricks to simplify the model before it even runs. Things like constant folding, pre-calculating parts of the graph that won't change, or redundant node elimination, removing operations that don't actually do anything during inference, like a dropout layer, which is only used in training. It also performs fusions, combining multiple simple operations like, say, a conv layer followed by an add or maybe a batch normalization into a single, more efficient hardware kernel.
Okay, those sound like smart automatic cleanups. But where does the hardware acceleration really come in?
That brings us to the central concept, the real accelerator. Execution providers, or EPs. Think of EPs as pluggable backends. Each EP integrates with a specific hardware acceleration library. So for example, you've got the CUAEP for NVIDIA GPUs, which leverages NVIDIA's cuDNN library. Then there's the TensorArt EP, also for NVIDIA GPUs, but it performs even more aggressive, deeper optimizations for potentially higher performance. If you're targeting Intel hardware, the CPUs, integrated GPUs, or their neural processing units, NPUs, you'd use the OpenVINO EP. And critically, there's always the default CPU EP. This acts as a universal fallback, ensuring the model can always run, even if no specialized hardware is available, or if some operations aren't supported by the fancy EPs.
That makes you wonder, though, what happens if one accelerator, say a GPU via the CUAAP, doesn't support every single operation in your complex model? Does the whole thing just fail?
No, not at all. And that's actually one of ORT's really clever features. It handles this with graph partitioning and heterogeneous execution. When you load the model and specify your preferred EPs, ORT queries each EP to see which nodes, which operations in the graph they can handle efficiently. The graph is then intelligently split into subgraphs. Each subgraph is assigned to the most suitable EP available in your priority list. Any operations that aren't claimed by one of your specialized EPs just automatically fall back to running on the CPU EP. So it mixes and matches, using the best tool for each part of the job. Exactly. This heterogeneous execution ensures your model always runs, while still pushing the maximum amount of computation to the fastest available hardware accelerators. But here's a crucial point about ORT performance. It's not entirely automatic. It's really about deliberate configuration. You have to explicitly select and configure the right execution providers for your target hardware and understand their trade-offs. For instance, the CEGU EP is generally broad, pretty easy to set up, good baseline GPU performance. But the Tensor EP can offer superior performance through more aggressive whole graph optimization and caching. However, it usually requires longer setup times, like building an engine, and it might support fewer operators out of the box compared to CEGU. So mastering OT really means mastering this EP configuration, understanding your hardware and choosing the right tools. Okay, that makes a lot of sense. We understand the why, the efficiency gap, and the what ONNX is the format, ORT as the runner with EPs. Now, how do we actually get our hands dirty? How do we start using ONNX runtime in a project? Right, the practical steps. The very first step is usually converting your trained model from its original framework. Let's stick with the PyTorch example, say a ResNet 50 image classification model into that ONNX format. For PyTorch, the standard way is using the torch.onnx.export function. What this function essentially does is it traces your model's execution. You feed it a sample input, and it runs that input through the model, recording the sequence of operations it performs. That recorded sequence becomes the ONNX graph.
Tracing. Okay. Are there important things to watch out for during that export?
Yes, definitely. You need to pay attention to a few key parameters in torch.onnx.export. Offset version is important for compatibility. It specifies the ONNX operator set version you're targeting. Defining clear input names and output names is a really good best practice for clarity later on. And dynamic axis is incredibly powerful. It lets you specify which dimensions of your inputs or outputs can have variable sizes, like the batch size or sequence length. Very useful for real-world applications. And of course, if you're starting from TensorFlow, there's a similar tool called TF2ONNX. After exporting, I can't stress this enough, visualize the exported.onx file with Netron. Seriously, just do it. It lets you visually inspect the graph structure, check inputs, outputs, and catch potential conversion issues early. It's an invaluable debugging step.
Okay, export done. Netron check passed. We have our .onNX model file. What's the next step to actually running it with ORT?
Now you bring in ONNX Runtime itself. The central component in Python is the Inference session class. You create an instance of this class, passing it the path to your .ONNX file. Critically, you also provide the provider's argument. This takes a list of execution provider names in order of preference. For example, you might pass CU to execution provider, CPU execution provider.
Prioritized, you said.
Yes, prioritized. ORT will try to use the first provider in the list, GUDA in this case, for as much of the graph as possible. If it encounters an operator that this UDEP doesn't support, it will automatically fall back to the next provider in the list, which is the CPU EP here. This fallback mechanism ensures the model runs, leveraging the GPU where possible. So just to quickly recap the EP trade-offs to help you choose that list: CUDA EP for NVIDIA GPUs, broad operator support, good out-of-the-box performance, generally low setup effort, a great starting point for NVIDIA hardware. Tensor EP, also NVIDIA GPUs, often the highest potential performance due to aggressive optimization and engine caching, but higher setup complexity, longer initial build times for the engine, and potentially more limited operator support than CD. OpenVINO EP for Intel hardware CPUs, integrated GPUs, NPUs, optimized specifically for Intel silicon, medium setup effort. CPU EP, your universal fallback, runs on any CPU, requires zero setup, but naturally offers the lowest performance compared to hardware accelerators.
This all sounds great for just getting a model running maybe on the CPU or getting a basic GPU speed up, but what about squeezing out every last drop of performance, especially on GPUs? I've heard whispers about something called IOBinding. Is that important?
Oh, absolutely crucial. You're hitting on a really key point for high-performance inference. Simply calling the session.run method and passing in, say, a NumPy array often hides a significant bottleneck data transfer. Think about it. That NumPy array typically lives in your CPU's RAM. If you're using the CUDA execution provider, ONNX Runtime has to implicitly copy that data from CPU RAM over the PCIe bus to the GPU's memory before the GPU can even start computing. Then after the computation, it often has to copy the results back from GPU memory to CPU RAM so you can use them in Python.
So lots of back and forth copying.
Exactly. And that copying takes time. On slower systems or with large data, that CPU-GPU data transfer can become the dominant factor, completely masking the GPU's computational speed advantage. I remember once spending ages debugging why a model wasn't much faster on GPU, and it turned out the data copying was eating all the gains. That's when I learned the hard way about IOBinding. IOBinding solves this problem elegantly. It enables what's called zero-copy inference. It provides an API that lets you bind data that already exists on the target device, like a PyTorch tensor, that you've already explicitly placed in GPU memory directly to the model's inputs and outputs within ORT. When you then call run with IOBinding, ORT can operate directly on that GPU memory without needing those expensive copies across the PCIe bus during the inference call itself.
So you keep the data on the GPU as much as possible.
Precisely. Achieving peak performance, especially for low latency or high throughput scenarios, requires designing your entire data pipeline loading, pre-processing, inference, post-processing to operate on the target device, like the GPU, whenever possible. This is actually a fundamental shift from typical CPU-centric Python workflows, where everything defaults to NumPy arrays and CPU RAM. It's essential for building truly high-performance AI applications with OT.
Okay, that's a critical insight for performance tuning. Now, once you can reliably run inference, maybe using IOBinding, the next frontier is usually making it even faster and more efficient, right? What are the first steps ORT takes automatically to give us speedups, even before we start doing more advanced manual optimizations?
Yeah, ORT has built-in capabilities for automatic speedups through graph optimizations. These are transformations applied directly to the model's computational graph before execution begins. The goal is to simplify the graph and reduce the number of operations, which often leads to significant performance gains with very little effort on your part. You can control the extent of these optimizations using the graph optimization level option when you create the inference session. There are a few levels. Ordinable Basic includes relatively simple, semantics-preserving rewrites. We mentioned some earlier. Constant folding, redundant node elimination, like removing identity ops or dropout nodes. It also includes basic node fusions, like combining a convolution with a subsequent add or batch normalization into a single, more efficient kernel.
And the higher levels.
Ordinable Extended builds on the basic level. It adds more complex fusions that are often hardware-aware. Examples include fusing GEMM, matrix multiplication operations with activations, fusing layer normalization components, and critically, especially for modern transformer models, this level includes attention fusion. This combines the multiple underlying operations of a self-attention block like mapmols, adds, softmax into a single, highly optimized attention operator kernel, which can give huge speedups. The default setting is usually Ordinable All, which applies all available optimizations.
Can these optimizations slow down the startup time?
They can, yes. These optimizations can be performed online, meaning every time you create an inference session. This adds a bit to the model loading and initialization time. Alternatively, you can perform these optimizations offline. You run the optimization process once and then save the optimized graph to a new .onNX file. For production scenarios, using an offline optimized model is generally recommended because it significantly reduces the startup latency each time your application loads the model.
Makes sense. Pre-compute the optimization. Now, these graph optimizations sound great for cleaning things up, but what if we need to radically shrink the model size or push performance even further? This raises an important question. Can we actually change the precision, the data type used within the model itself to achieve that?
Absolutely. And that brings us to the art of quantization. This is arguably one of the most effective and widely used model compression techniques available today. At its core, quantization is the process of converting a model's parameters, primarily its weights and sometimes its activations, from high-precision floating point numbers, usually 32-bit, FP32, down to lower precision data types. The most common target is 8-bit integers, or INT8.
So reducing the number of bits used to represent each number.
Yes, exactly. Think of it like taking a high-resolution photograph and saving it as a smaller JPEG. You lose some fine detail, but if done carefully, the overall picture remains recognizable. You save a lot of space and it loads faster. The benefits of quantization are pretty substantial. First, you typically get around a 4 times reduction in model size when going from FP32 to INT8. That means less disk space, less memory footprint during runtime. And critically, you often see 2x to 4x faster inference speed.
Why fast?
2 main reasons. Modern hardware, especially CPUs and specialized accelerators like NPUs or tensor cores on GPUs, can perform integer arithmetic much faster than floating point arithmetic. And second, because the data is smaller, 8 bits versus 32 bits, you're moving less data around between memory and the compute units. This reduces memory bandwidth bottlenecks, which are often a limiting factor. Mathematically, the most common approach is linear quantization. You map a range of real floating point values, R, to a range of integer values, Q, using a scale factor S and a 0 point Z. The basic equation is R SEQ QZ. The scale tells you the step size between quantized values, and the 0 point ensures that the real value 0.0 is mapped exactly to an integer value, which is crucial for operations like real U activations or zero padding and convolutions. There are nuances, of course. Things like symmetric versus asymmetric quantization is the range centered around 0, and per tensor versus per channel granularity. Per channel is often better for convolutional layers, using a separate scale and 0 point for each output filter channel, which usually improves accuracy compared to using one scale for the entire weight tensor.
Okay, the theory makes sense. Smaller numbers, faster math, less data movement. So how do we actually do this quantization in practice with ONNX Runtime?
The most common starting point is post-training quantization, or PTQ. As the name suggests, this is applied to an already trained FP32 model, and crucially, it doesn't require any retraining or fine-tuning of the model. Already offers 2 main PTQ methods. The easiest way to get started is dynamic quantization. With dynamic quantization, the model's weights are quantized offline, converted to INT8, and stored in the .onNX file. However, the activations, the values flowing between layers during inference, are quantized on the fly at runtime. Already calculates the scale and 0 point for the activations dynamically based on the observed range of values for each specific input that comes in.
So it adapts to the input data.
Exactly. This adaptability often leads to better accuracy than static quantization, especially for models where activation ranges vary significantly, like many transformer-based models, BERT, GPT variants, Whisper, and RNNs. Dynamic quantization is particularly good for models where memory bandwidth for loading the large weight tensors is a bottleneck because the weights are stored compactly as INT8. And the API call in ORT, Quantis Dynamic, is usually very simple.
Okay, dynamic sounds convenient. What's the other main PTQ method?
The other method is static quantization. This typically offers the highest performance because both the weights and the activations are quantized offline and use fixed scale and 0 point values baked into the model. However, it requires an extra crucial step called calibration.
Calibration, what's that involve?
Calibration involves feeding a small but representative data set through the original FP32 model. While this data flows through, you observe and record the typical range, min and max values, for the activation tensors at various points in the network. These observed ranges are then used to calculate the fixed scale and 0 point values for the activations, which get embedded into the final quantized INT8 model. To do this in OI, you need to implement a simple Python class called a calibration data reader that provides this sample data set to the quantization tool.
And how do you choose the best way to calculate those scales and 0 points from the calibration data?
There are several common calibration methods you can choose from. Min-max, simplest and fastest. Just uses the absolute minimum and maximum values observed during calibration. But it's very sensitive to outliers. A single unusual activation value can skew the range and hurt accuracy, entropy, or KL divergence. These methods try to find a quantization range that minimizes the information loss between the original FP32 distribution and the quantized INT8 distribution. There are generally more robust outliers and often yield the best accuracy, but they take longer to compute during the calibration process. Percentile, a practical compromise. It uses percentile values, inches in the 1st to 99th percentile, to determine the range, which makes it more robust to outliers than min-max, but faster than entropy KL divergence.
So there's a trade-off between calibration time, robustness, and potential accuracy.
Exactly. And one more important concept in modern static quantization workflows, particularly in ONNX, is the quantize-dequantize QDQ format. Instead of completely replacing an FP32 operator like conv with a special integer-only operator like qlinear-conv, the QDQ approach inserts quantized linear and dequantized linear nodes around the original FP32 operator in the graph. So an FP32 conv becomes quantized linear, conbiased, quantized linear.
Why do that? It sounds like more operations.
It seems counterintuitive, but it's actually very beneficial. This structure allows the underlying conv operation to still be executed using highly efficient INT8 kernels by the hardware backend, like CUDA or OpenVINO. But it keeps the overall graph structure very similar to the original FP32 model. This makes it much easier for hardware backends to recognize patterns and apply their own optimized fusions across these QDQ blocks. It simplifies backend implementation and often leads to better performance. The key takeaway here, though, for any quantization approach is that it's not a simple one-click compilation like compiling code. It's really more of an empirical science. The optimal strategy dynamic versus static recalibration method per tensor versus per channel depends heavily on your specific model architecture, your target hardware, and crucially, how much, if any, accuracy drop you can tolerate. Experimentation and rigorous benchmarking of both performance and accuracy are absolutely crucial.
That's a really important point. It's not magic. It's engineering with trade-offs. So what happens if you go through all this optimization, graph optimization, maybe static quantization with careful calibration, and your model's accuracy takes an unacceptable hit? Is it just a dead end for those performance gains? Do you have to go back to FP32?
No, thankfully, it's absolutely not a dead end. ONNX Runtime and the broader ecosystem provide more advanced tools specifically for diagnosing and rescuing your model's accuracy after quantization. Debugging quantization accuracy degradation is really a systematic investigation. First, you need good baselines. Measure your original FP32 model's accuracy on your evaluation dataset. Then measure the accuracy of your naively quantized INT8 model. Quantify the drop. Next, you try to isolate the source of the error. Is it primarily the weight quantization causing issues, or is it the activation quantization? Sometimes you can test this by quantizing only one or the other. The really critical step is to identify the specific problematic layers in your network. Which layers are most sensitive to quantization and introducing the most error or quantization noise. ONNX Runtime actually provides a quantization debugging API to help with this. You can use functions to compare the outputs or weights of individual layers between the FP32 and quantized models, calculating metrics like signal to quantization noise ratio, CQ&R, or mean squared error, MSE, per layer. This pinpoints the culprits.
Okay, so you can find the sensitive layers. What do you do then?
Once you've identified them, the most common strategy is to apply mixed precision quantization. This means you configure the quantization tool, like ORT's quantizer, to keep those specific sensitive layers in their original FP32 precision while quantizing the rest of the model to INT8. You typically pass a list of notice to exclude from quantization. This creates a hybrid model, mostly fast INT8, but with critical parts remaining in high-precision FP32. This often allows you to recover most, if not all, of the lost accuracy, while still retaining a significant portion of the performance benefits. It's a very practical balancing act.
That sounds like a great fallback. But what if even mixed precision PTQ isn't enough to get the accuracy back where it needs to be?
Right. If post-training quantization, even with mixed precision, still results in an unacceptable accuracy drop, then the most powerful technique available is Quantization-Aware Training, or QAT. Unlike PTQ, which happens after training, QAT simulates the effects of quantization during the model training or fine-tuning process itself. How it works is you insert fake quantiz nodes into your model graph during training. These nodes mimic the rounding and clamping effects of INT8 quantization during the forward pass calculation. But crucially, during the backward pass, when gradings are calculated for learning, they use a clever mathematical trick called the straight-through estimator, STE. This essentially allows the gradients to pass through the fake quantization node as if it weren't there, enabling the model to learn.
So the model learns to compensate for the noise quantization will introduce.
Exactly. The model learns weights that are inherently more robust to the noise and precision limitations of INT8 arithmetic. Because the model has adapted during training, QAT almost always yields significantly higher accuracy for the final quantized INT8 model compared to any PTQ method. Frameworks like PyTorch have built-in support for QAT workflows. You typically prepare the model, fine-tune it with the fake quantization active, and then convert it to a truly quantized model for deployment. It's more involved than PTQ, but it's the go-to method when accuracy is paramount.
That's an impressive toolkit for rescuing accuracy. It seems like there's always another technique to try, but I've also heard there are even more advanced ways to shrink models, maybe working alongside quantization or even instead of it sometimes. What else is out there in the broader compression landscape?
You're right, quantization is just one piece, albeit a very important piece, of a much larger model compression toolkit. There are several other major techniques. One is pruning. This involves removing redundant parameters, weights, or even entire structures from a trained network. There's unstructured pruning, where you remove individual weights based on some criteria, like having a small magnitude. This creates sparse weight matrices. The challenge here is that you often need specialized hardware or libraries that can efficiently compute with sparse matrices to actually see a speedup. Then there's structured pruning, where you remove entire groups of parameters, like entire filters in a convolutional layer or neurons or attention heads. This results in a smaller but still dense model architecture. This is often more practical for achieving speedups on standard hardware without special sparse computation support.
Okay, pruning removes parts. What else?
Another powerful technique is knowledge distillation, often abbreviated as KD. This uses a teacher-student paradigm. You start with a large, complex, highly accurate teacher model. Then you train a smaller, more efficient student model. The key is that the student isn't just trained on the ground truth labels, it's also trained to mimic the outputs, the logits before the final softmax, or even the intermediate feature representations of the larger teacher model. This gives the student a much richer, more informative training signal than just the hard labels, often allowing it to achieve surprisingly high accuracy for its much smaller size.
Teaching the small model the soft knowledge from the big one.
Precisely. And finally, especially relevant for today's massive language models, we're seeing the rise of techniques like low-rank adaptation, LoRa, and its quantized counterpart, QLoRa. These fall under the umbrella of parameter-efficient fine-tuning, or PEV. The core idea of LoRa is that instead of fine-tuning all the billions of parameters in a large pre-trained model, you freeze the original weights and inject small, trainable adapter matrices, low-rank updates, into certain layers, like the attention layers. You only train these small adapter matrices, which drastically reduces the number of trainable parameters and the memory required for fine-tuning, often by orders of magnitude. QLoRa takes this even further by combining LoRa with aggressive 4-bit quantization of the frozen base model weights. This reduces the memory footprint so much that it becomes possible to fine-tune truly massive models with tens or hundreds of billions of parameters on a single consumer-grade GPU. It's quite revolutionary for democratizing LLM fine-tuning.
Wow, 4-bit, that's aggressive.
Extremely. And the real magic often happens when you start combining these techniques. True optimization mastery often lies in finding the right recipe. Maybe you prune a model first, then use knowledge distillation to recover some accuracy in a smaller student, and finally quantize that student model using QAT or PTQ for deployment. They're often complementary.
Okay, this all sounds like some serious theoretical wizardry. But let's bring it back down to earth. How does all this apply to a real-world project? Can you walk us through an example, maybe putting several of these pieces together?
Absolutely. Let's design a sort of capstone project to illustrate the process. Building a real-time audio transcription service using OpenAI's Whisper model. The project goal is clear. Create a web service that can take an audio file and return a transcription quickly and efficiently so. High performance, low latency. We'll leverage a pre-trained ONNX version of Whisper, which is readily available. Step one is always baseline benchmarking. We need to know where we're starting from. So we take the standard FP32 Whisper ONNX model and measure its performance. Let's say on a decent CPU, the FP32 model, maybe the base or small version, has a size of around 150 millibit, and processing a standard audio sample takes about
1.25 seconds. That's our CPU baseline latency. Now we test it on a GPU using the CUDEP. Same 150 millibeat model size, but the latency drops significantly, maybe down to around 0.3 seconds. Much better, but maybe still not fast enough for real-time interaction.
Okay, baseline established. Now for the optimization part.
Right. Next comes optimization. Since Whisper is a transformer-based model, we know from our earlier discussion that dynamic quantization is often a good fit, especially for balancing ease of use and accuracy. So we'd use ONNX Runtime's Quanti's dynamic tool. Whisper typically has two main components, an encoder and a decoder. We had applied dynamic quantization to both, converting their weights to INT8. After quantization, we re-benchmark and analyze the results. We expect the INT8 model size to drop dramatically. That 150 millibeat FP32 model might now be only around 40 millibeat. That's our 4x size reduction right there.
And the speed?
The speed should improve too. On the CPU, that 1.25 second latency might drop to maybe 0.65 seconds, a nice speed up. On the GPU, the 0.3 second latency might improve further, perhaps down to 0.22 seconds. The GPU gains from quantization are sometimes less dramatic than CPU gains if the model was already GPU bound. But reducing memory bandwidth pressure often still helps. Now, for a real production system, this is where you'd pause and rigorously evaluate the accuracy of this INT8 model. For Whisper, you'd use metrics like word error rate, WER, on a standard test set. If the accuracy drop was too large, you'd then circle back to techniques like mixed precision PTQ, maybe keeping parts of the decoder in FP32, or potentially even QAT if necessary.
Assuming the quantized model meets our accuracy and performance goals, what's the final step?
The final step is deploying the optimized model. A common way to do this for a web service is using a Python web framework like FastAPI. You create a basic main.py script. In the script, you initialize your FastAPI application. On application startup, you load your quantized INT8 ONNX models, encoder and decoder, using Inference session. Here you choose your target execution provider, maybe CPU execution provider if deploying on CPU-only instances, or CUDA execution provider if deploying to GPU servers. You'd also load any necessary pre-post processing components, like the Whisper processor tokenizer. Then you define an API endpoint, say transcribe. This endpoint would accept an uploaded audio file. Inside the endpoint function, you'd pre-process the audio, the example using Librosa to resample and get MEL spectrograms, run the ONNX encoder session, then run the ONNX decoder session autoregressively to generate the text tokens, and finally decode the tokens back into human-readable text. You return that transcription text in the API response.
And running that service.
You could run it locally for testing using an ASGI server like Uvicorn, something like Uvicorn main.app reload. For a real production deployment, you'd almost certainly want to package this entire application, your Python code, the ONNX models, dependencies into a Docker container. This makes deployment much more reliable and scalable, whether you're deploying to the cloud or on-premise servers.
Wow, okay. That really connects all the dots. From benchmarking to optimization to actually serving the model, we've covered so much ground today. From understanding the challenges of that AI efficiency gap to leveraging ONNX as the common language and ONNX Runtime as the accelerator, getting into practical conversion, the importance of zero-copy IOBinding for GPUs, the automatic graph optimizations ORT gives you, and then the whole art and science of quantization dynamic versus static calibration QDQ. And finally, putting it all together in that real-time transcription service example, it's a lot.
It is a lot, but it's a journey you've now taken. You've seen how to bridge that gap between a trained model and efficient production deployment, understanding the format, ONNX, the engine, ORT, and its EPs, the practical steps of conversion and running inference, and then the crucial optimization techniques like IOBinding, graph optimization, and especially quantization. You really do now have the foundational skills for tackling production-grade ML engineering and optimization.
Absolutely. This deep dive has definitely armed you, the listener, with some powerful tools and concepts. And of course, your exploration doesn't have to stop here. For those of you looking to go even further, there are lots of potential next steps. You could actually try deploying that optimized Whisper model we talked about, maybe onto a really resource-constrained edge device like a Raspberry Pi or an NVIDIA Jetson, see what challenges arise there. Or you could explore ONNX Runtime Web, or TO Web, which lets you run these optimized models directly in the user's web browser using WebAssembly and WebGL or WebGPU for acceleration. Very cool for client-side AI. On the optimization front, you could experiment with combining quantization with some of the other techniques we mentioned, like structured pruning, to push efficiency even further. And if you're feeling particularly adventurous, you could delve into more aggressive quantization, exploring those sub-8-bit techniques like INT4 or block quantization, which are becoming increasingly critical for handling the sheer scale of the latest massive language models.
Yeah, and if we just step back and connect this to the bigger picture for a moment, it's crystal clear that as AI models continue to grow in complexity and become more ubiquitous, woven into more and more applications, the ability to effectively optimize and deploy them efficiently is no longer just an afterthought or a nice-to-have. It's rapidly becoming a core competency. It's what actually shapes the real-world impact and feasibility of these powerful AI technologies.
So maybe the provocative thought to leave you with is this. With AI models growing ever larger, are we actually entering an era where the true innovation, the bottleneck to progress, lies not just in creating newer, bigger models, but perhaps even more so in the art and science of shrinking and speeding them up? In turning that impressive research into practical, accessible, efficient technology that can run anywhere for everyone. Something to think about until our next deep dive.